Okay, now we are going to prove that they are equivalent. The proof strategy is the following. We will first prove that the first four are equivalent by showing that 1 implies 2, and 2 implies 3, and 3 implies 4, and 4 implies 1. And secondly, we'll prove that 2 and 5 are equivalent. And this will show that 1 through 5 are all equivalent. So first, let's show that 1 implies 2. Here are the statements of 1 and 2. Assuming that T is ergodic, and remember by definition this means if T inverse of B is B, then we have the measure of B is either 0 or 1. And that is the definition. Now, to prove 2, we'll take any measurable subset with this property, that the symmetric difference of B and T inverse B has measure 0. So let B be an so-called almost invariant measurable subset. And this precisely means that the measure of this symmetric difference is 0. And our goal is to construct an invariant set utilizing B. And so here is the tricky part. How is that set constructed? Let C be equal to the intersection from capital N equal to 0 to infinity of the union of N equal to N to infinity of T raised to the power negative N applied to B. And recall that you may have learned in the abstract matter theory that this set is the lim superset of this sequence of sets. So recall this is called the lim superset as n goes to infinity of this sequence of sets. Although we are not going to use this, it is worth mentioning this because this might confuse you at the beginning. Now, C, we claim, is T invariant because the inverse map can break through all the intersections and unions and apply to each term directly. And that is a very good property of the inverse. So this is equal to intersection of union of T raised to the power negative N minus 1 applied to B. And this, by shifting the index by 1 for this union, you will get that this guy is equal to the intersection of unions where n starts from n plus 1 to infinity of T raised to the power negative N of B. But I will tell you this is same as C. Do you see why this is same as C? That is because although we are taking the union of sets with one less member, we are taking the intersection of infinite many of them anyway, eventually. So If we just miss one member in here, after we take the intersection from n equals 0 to infinity, this won't matter. And this union will decrease with n anyway. So this is the same as C. And this proves that C is T invariant. And now it follows immediately from here and the definition of ergodicity that mu of C will either be 0 or 1. So this implies mu of C is 0 or 1. It should be clear to you that this C is also measurable because T is measurable because T is a measurable map and you are taking multiple unions and intersections. So this is still in the sigma algebra. Our next goal will be try to associate the measure of C with the measure of B. It turns out that the measure of C is same as the measure of B. So now we claim that mu of C is equal to mu of B. And once we verify this claim, then we are done. Because the goal is just to show that mu of B is either 0 or 1. In order to prove this, we observe that it suffices to prove that the symmetric difference of C and B has measure 0. By measure theory, once this is proved, then you know B and C must have same measure. And the proof of this will involve some set theoretical manipulations. And we will do this carefully. So first observation is that for any n greater or equal to 0, we have this metric difference of B with this union is contained in the union from n equal to infinity of this metric difference. Why this is true? Because if we take an element from here, there are only two possibilities. Either it will be in B, but not in this union. In that case, it will be in B, but not in any member in here. So in particular, it will be in B and not in some member in here, which means it will be in the union of this. The second possibility is that that element from here is from this union, but not from B. But in that case, that element must come from one member, at least one member from here, but at the same time not in B. So it will be in one member here, but not in B. That also proves that element is in the union of this. I hope this is very easy for you to verify, so I just talked through without writing it down. So this fact should be easy for you to check. Second, the measure of B symmetric difference is t raised to the power negative n applied to B is 0 for all n greater or equal to 1. So why is this true? You should expect this because by our assumption, we already assume that the symmetric difference between B and T inverse B has measure 0. Now you just replace this T negative 1 to T raised to the power negative n. So actually I should write this as a subclaim. this needs some efforts to prove. To show this, you need to observe that the symmetric difference of B and T inverse T raised to the power n, the symmetric difference of B and T raised to the power negative n applied to B is a subset of this union, I from 0 to n minus 1 of the members T negative I B symmetric difference is T negative I plus 1 B. This containment can be verified by induction. So the first step that you want to do is that you want to show this symmetric difference is contained in the union of B symmetric difference with T raised to the power negative n minus 1 applied to B. And this T negative n minus 1 B symmetric difference with T negative nB. So why is this containment true? This is true because you can consider several cases. So pick the point from here, then it must be one of B or T negative nB. And you also want to consider the cases whether that point is also in T negative n minus 1 applied to B. So X could be in B but not in T negative nB. In that case, it might be in here or not in here. And another case that it is not in B but in T negative nB. And in that case, it might be in here or not in here. So totally, there will be 4 cases to consider. For the first case, X will fall into this set, the symmetric difference of T negative n minus 1 and T negative n, because it is in here but not in here. So it falls into this. In the second case, X will fall into here because it is in B but not in T negative n minus 1B. So it will be in here. In the third case, it will fall into this set because in the third case, it is in T negative n minus 1B but not in B. In the fourth case, X will fall into here because it is in T negative n but not in T negative n minus 1B. So we just check those 4 cases and thus verified this containment. And you know how to do next. Next, we're going to apply the induction to this first part. Now you have lowered this index by 1, and you can use induction to this part to conclude this containment. And that is a proof. Okay, so what does this containment tell you? Remember that we want to prove this subclaim that the measure of this set is 0. Now we put this inside a union of some sets, and you might be able to observe that this guy So each member in this union has measure 0 due to our assumption. So this part has measure 0. Why is that? Because the measure of this by the measure preserving property of T, because we assumed that T is always measure preserving. And you know, because the inverse of a map has a good property that it commutes with any set theoretical operations. So this guy is same as the symmetric difference of B and T inverse B. And this guy, by our assumption here, is equal to 0. So each member here has measure 0. So this guy has measure 0. And this verifies our subclaim. And next, we'll try to prove this. The proof strategy for this is that we're going to choose a sequence that approximates C. And each member in that sequence has symmetric difference with B of measure 0. So this strategy is pretty common in measure theory or real analysis in general. To prove an inequality, you choose something that satisfies the equality and it approximates some target in that equality you want to prove. So now looking at the definition of C, can you think of a way to choose that approximating sequence? I'll let you think about it for a while, but I will tell you the answer anyway. So it shouldn't be too hard for you to see how to choose that sequence just from the definition of C. Now here's how you're going to choose that approximating sequence. We're going to take this part, the union starting from n equal to n to infinity. And you know if you take the infinite intersection, you get C back. That is how this guy approximates C. Now let me write this down carefully. So we take C sub n to the union from n equal to n to infinity of T negative n applied to B. So you know that this set is nested, which means C0 contains C1, contains C2, and so on. And it descends to C. Namely, if you take the infinite intersection, it gives you precisely C. And furthermore, if you take the symmetric difference of C sub n and B, what do you get? What you get is that this union of T inverse B's symmetric difference with B. And if you take the measure of this, remember, we just proved from above that this is equal to 0. What I mean is that we just proved this subclaim where symmetric difference of B and T inverse B has measure 0. And this guy is contained in the union of those individual terms. So This follows precisely by our argument above. And this proves that Cn's metric difference with B has measure 0. And what you do next is that you are going to take the limit of this guy. There will be some set theoretical operations. There will be unions and complements. And remember, because mu is a probability measure, it is a finite measure. So the limit taking operation always commutes with this mu, no matter you take the intersection or the union. So it is safe to just put the limit inside and conclude that the symmetric difference of C and B has measure 0. And that completes the proof of the direction from 1 to 2. Because remember, once we prove this, then mu of C is equal to mu of B. And because mu of C is concluded at the beginning that it is either 0 or 1. So it follows that mu of B is also either 0 or 1. And that is what 2 is talking about.